In this video, I'll consider gravitational potential energy, work done by gravity, mechanical energy, and how to deal with friction. I'll also just consider gravitational potential energy in generalized. So let's dive into that. So considering gravitational potential energy, we can start by just saying it's mgy. That's a force times a distance. Well, here comes our piano of AP physics of mass m, and it has gravitational potential energy at position 1, so I'm calling that UG1, and then UG2. Work done by gravity in moving it from position 1 to position 2. Recognize that gravity acts downward and it's moving downward. They're both in the same direction, therefore the work done by gravity is positive. How about the change in gravitational potential energy? Well, intuitively, you know it's less at the final position than at the initial position. So the change is negative. It's gone through a reduction in gravitational potential energy. Therefore, it's pretty safe to say that work done by gravity is not equal to the change in potential energy. One's positive, one's negative. Rather, work done by gravity is the same thing as what the gravitational potential energy was compared to what it is. So it's 1 minus 2, which is the opposite of the change, because change is final minus initial, 2 minus 1. Now we have 1 minus 2. So that's the negative change in gravitational potential energy. Well, now let's consider going the other way. We start position 1 at the bottom and move it up to the top. Doesn't matter how it got there, it's moved from position 1 to position 2. The question is, what kind of work does gravity do? Gravity doesn't obviously take it up there, but as the piano is taken from position 1 to position 2, gravity certainly does work on it, because it's tugging down on it the whole time, and it moves anti-parallel to that direction. So, work done by gravity is negative. And the change in gravitational potential energy, well, let's see, it went from a lower value to a higher value. So that's a positive change. Work done by gravity, again, logically is not the change in u sub g, but the negative change in u sub g. And now on to mechanical energy. What's mechanical energy? Well, it's just kinetic and potential. At this point, we're just discussing gravitational potential, so we'll limit our discussion to that. But keep in mind that any kind of potential energy, well, I got to be careful. If it's associated with conservative forces, which we'll discuss a little later, then that potential energy is, if it's conservative, it's from a conservative force, like springs, which is something we'll consider, then that potential plus the kinetic is mechanical. So let's consider a falling piano. We have gravitational tug acting on it, and it's accelerating. Total work done on the piano, delta K. Keep in mind the work energy theorem. It continues and will continue to be a very valuable reality for us to consider in our problem solving. So it's K2 minus K1. Work total is work done by gravity. There is no other work being done because it's the only force acting on the piano. We are ignoring air friction. So that's equal to negative change in potential energy. So the total work is negative delta U sub G, and it's also delta K. So those two things are equal. Therefore, delta K plus delta U sub G equals, you guessed it, 0. Now keep in mind, again, this is only when mechanical energy is conserved. In other words, you don't lose any total amount of this quantity K plus U sub G. So in other words, there's no frictional forces involved that's reducing the amount of mechanical energy. So with that in mind, we can expand delta K and delta U. Delta K is K2 minus K1. Delta U sub G is UG2 minus UG1. And we bring the 1's over to one side and the 2's over to the other side, and we have all the kinetic energy at position 1 and plus I should say all the energy at position 1, kinetic and potential, is equal to all the energy at position 2, kinetic and potential. Wonderful problem solving technique or reality to keep in mind, to keep track of energies at various positions. Why is this thing useful? Well, in part at least, because the potential energy is a lot easier to track or keep track of than the change in kinetic energy. Kinetic energy is associated with speeds. U sub g is associated with position, which is easier to measure than speeds typically. And once you know everything you need to know about U sub g, then because added to delta k at 0, we can then discover delta k. Well, the position is arbitrary when we're talking about gravitational potential energy. Y2 minus Y1, the difference in position can be the same even though the values are much different. In other words, it's constant. So this piano could have gone from, say, could go from this position here down to this position, or we could start here and go down to this position. And if the change is the same, then the change in gravitational potential energy is the same. Of course, those two scenarios had a lot of difference in the actual values of UG1 and UG2. If we're talking this point and this point, those values are a lot less than this point or position and this position. So the values themselves are important, are unique, but the difference in the values is not. The change in U sub g doesn't matter. Now, typically we want losses to be minimized, but in the real world we live in, we generally can't bring friction down to 0. So the mechanical energy is the combination of kinetic and gravitational potential. So here's the falling piano, and gravity's tugging on it with mg, but this other force, namely frictional force in this case, will be applied to it also. So the mechanical energy can change. These values actually can change. So the mechanical energy is going to be changed by this other force acting on it. So the change in mechanical energy is delta k plus delta U sub g. Now this delta here, these deltas, these changes, combined with other work, here's work other, something else other than the change in kinetic plus potential, you can consider those changes to be 0. All right, but it doesn't mean that the change in mechanical energy is 0, because this other work can either add or subtract to the total amount of energy. So delta E really just comes down to work other. So if there is a change, other work has been done, not something other than kinetic and potential energy change. All right, so this is friction, it's applied force, or something like that. It can be positive, it can be negative, it can be 0. 0 is self-evident. Negative is typically associated with friction. What about positive? Well, it's like a rocket thruster engine, so an applied force. You can externally put a rocket engine on this piano and shove it downward along with gravity to increase its mechanical energy. And then the delta E in that case is going to be increased. There's going to be a positive change. So let's consider generalizing the gravitational potential energy over a curved path. And there's our object. It's a nice, healthy-sized bug with mg acting straight down and is going around this path here, so we've got some other force acting on it. And we're going to show a little more detail here. Position of the bug. We have motion along the path delta s. You can consider that ds at that point. So we have a delta x and a delta y associated with delta s, with the weight acting straight down. And we want to consider the work done over delta s, the work done by gravity. So across this little distance, what does gravity do? Well, this won't be too profound. You probably can guess what the result is going to be. Work done by gravity is mg dot delta s, so force dotted with displacement. But of course, this displacement, being at an angle, has a y and an x component. And you probably know the one that's important. We are talking mg, which is in the direction j, dotted with delta s. Delta s has the components delta xi plus delta yj. When we dot j with I, we get 0. When we dot j with j, we get 1. So this becomes, since the direction is negative j, mg delta y. And that's u1 minus u2. That's the difference in potential energy going across any particular delta s. And so that's negative delta u. So our work done by gravity is negative delta u, which we already knew that, didn't we? We know that delta x does not contribute anything to this. Neither does F other, because we're just considering what's happening to the gravitational potential energy. All right, we're going to consider a problem here with a bull moose, because we haven't done that for a while. So here's a ramp, and here comes the moose. Yes, that is actually the sound of a moose. This is a ramp of radius r, and the bull moose is going to slide down and be moving at speed v at the bottom. So we're going to figure out the work done by the frictional force. So this is a rough ramp. It's not smooth or frictionless. Now that could get kind of complicated in detail, but we'll just be looking at it in general terms here. So we have at position 1 the weight of the moose, the gravitational potential energy mgr, the radius is basically the height, with the reference gravitational potential energy being 0 at the bottom. No initial velocity, therefore no initial kinetic energy. At an intermediate point, the moose has the same weight, but now there's a normal force, so that causes a friction to arise. There's a frictional force, which of course is slowing it down, removing mechanical energy. And then it also gets to the bottom. You ready for that sound one more time? Well, ready or not, here it comes. There we go. The moose is very happy to be sliding very quickly, and a maximum normal force right now. Notice the normal force is really big. It's got to overcome weight plus provide all the centripetal force needed as it just prior to leaving the circle, and then it immediately just becomes weight. The normal force becomes equal to the weight a moment later here. So this is the point still in the circle but just leaving, and therefore the frictional force is the greatest also. So you can imagine the friction force varying along here, and that becoming a fairly difficult problem to analyze in detail unless you know the conditions everywhere along the arc, which you could conceivably do. So there's some speed at the end, therefore there's a kinetic energy, and the gravitational potential energy is 0. So the total work is delta K, and the work done is gravity does work, and there's work other, namely friction. So we can rewrite this and say work other plus work done by gravity is negative delta u sub g, so that's equal to delta K. So work other, solving for it, is delta K plus delta u sub g. So delta K, K2 minus K1, delta U sub G, UG2 minus UG1. That is work other. There is no K1, there is no UG2, so we have 1/2 mv squared minus mgr is the total work other. Now that's actually fairly intuitive, because if you think about it, here we have all the energy in the system is contained in mgr, the gravitational potential energy. That's all going to convert to 1/2 mv squared at the bottom, but reduced a little bit. So 1/2 mv squared should be a little bit less than mgr because of friction. So this expression, this equation, is going to give us a negative value. Work done by friction equals mv squared over 2 minus gr. Of course, that will be negative. So that's the ramp with a moose sliding down on it, the analysis thereof, and I hope you enjoyed it.